Okay, so in this video, we're going to look at some integrals involving trigonometric functions, and in particular, integrals involving sine and cosine. So there are essentially three circumstances that we can encounter that require slightly different techniques. We can have an odd sine function, we can have an odd cosine function, or we can have both sine and cosine functions being even. In the circumstance where you have both sine and cosine are odd, then you can actually use either of the two strategies that we're going to talk about for odd sine and odd cosine. But we're going to look at examples in particular where one is odd and one is even. Now, you will need some identities in order to do these problems. For instance, you need the Pythagorean identity. We're going to use that in order to replace, if we have a lot of different trig functions in our expression, to replace other copies of the functions we want to get rid of. We're going to use the Pythagorean identity. It obviously only works for even powers of functions. And then also, if we have some standalone even functions in this last scenario, then we're going to need these two power reducing identities so that we can reduce square powers of cosine, even powers of cosine, to linear powers of 2 cosine, or cosine 2x. Now, sometimes in certain examples, you may need to apply these identities more than one time, but it's going to depend on the particular powers involved in the problems. In most cases, applying them twice is not crazy. If you're starting to apply them 3 times, then you may be doing it wrong. Or it's just a really unreasonable problem. All right, so let's look at our first example, an example with an odd sine function. Now, in this particular case, we have sine cubed cosine x squared. Now, in the case of an odd sine function, what we're going to do is we're going to split our integral up. We're going to actually split the sine function up into 1 sine x, and then the sine squared x will still be there, and then the cosine squared x. Now, the odd function is important here because that's actually the part that's going to determine what our antiderivative is going to be. So here, we're actually going to choose u, not u to be sine x, but du is sine x, because that's the odd one out. And then from that, that means that u has to be cosine x. Now, technically, of course, the derivative of cosine x is minus sine x, but I'm going to put the minus sign on the other side because I don't have minus sign. I have just positive sign. But this is how I'm going to choose my function that I'm going to do for my substitution, because I can convert my sines, my even powers of sines, to cosine using my Pythagorean identity. So that's actually what we're going to do next. So I'm going to rearrange things just a little bit. The sine squared x, I'm going to rearrange this in order to replace that with 1 minus cosine squared x. I still have my cosine squared x from before, and then my sine x dx is now going to be replaced by my negative du. So I've collected those on the end. And so now what I can do is I can actually make my substitution. So 1 minus u squared times u squared times negative du. I can pull my negative sign out, and I can distribute my u's, and that's going to give me u squared minus u to the fourth du, which is very easy to integrate using the power rule. And so I'm going to end up with 1/3 u cubed minus 1/5 u to the fifth plus c. And of course, I have to go back to my original variable. And so when I put everything back together, I get cosine cubed x plus, because I'm distributing my minus sign, 1/5 cosine to the fifth x plus c. So I'm getting essentially a polynomial in cosine. Now let's look at another example that is basically similar in concept, but now we're looking at odd cosine. So in this particular example, I have cosine to the fifth, but I've got some weird power of sine. The fact that sine is weird doesn't matter. It can be fractional powers, it can be even powers, it can be odd powers, whatever. As long as I have a odd function of cosine, odd power of cosine, then I can apply basically the same idea, the same strategy, but now I'm going to pull out my one extra cosine. So I'm going to pull out my cosine, and then I'm still going to have cosine to the fourth. Oops, forgot my s. Cosine to the fourth, and I'm still going to have, and I'm going to rewrite this, sine to the 1/2. And again, what I'm going to claim here is that I can let u be du basically be cosine x. The odd one is my derivative, and then u is sine x. And again, check your signs. The derivative of sine x is positive cosine, so I don't have a minus sign to deal with here. And then I can make my substitutions after I replace my cosine to the fourth using the Pythagorean identity. Now, keep in mind, cosine to the fourth is cosine squared squared. So this will be 1 minus sine squared squared. So again, keep in mind, 1 minus sine squared x is cosine squared, but I have cosine to the fourth. So that's cosine squared squared. And so I'm going to have to distribute this at some point. I still have my sine to the 1/2 x. And then my du is my cosine x dx. And so now if I make my substitutions, I'm going to get 1 minus u squared squared u to the 1/2 du. And now I'm going to have to do my foiling. It's honestly a little easier, I think, to do your substitutions and then do your foiling. It's a little bit less work because u is a lot easier to write than sine of x. And it just is algebraically a little bit simpler if you want to do that. Now, let's see, foiling this out. Remember, you can't distribute powers. You have to use the perfect square binomial rule. So this will become 1 minus 2u squared plus u to the fourth. And we're still being multiplied by u to the 1/2. And that's going to give us u to the 1/2. minus 2u. 2 plus a half is 2.5, which is 5/2. And then u to the 4th is 4 plus a half is going to be 4.5, which is 9/2. And when we do our antiderivative, add 1 to the power, we're going to get u to the 3/2. That was not what I wanted it to do. Times the reciprocal, which will be 2/3. And then minus, this u will become 7/2. Oops. And then I'm going to take my 2, and I'm also going to multiply it by 2/7. And then plus my 9/2 will become 11/2. And so this will get multiplied by 2/11 plus c. And if we put, again, we can't leave it with u, have to put everything back in x. So this will become 2/3 sine to the 3/2 x minus 4/7 sine to the 7/2 x plus 2/11 sine of 11/2 x plus c. So again, we have an expression that's entirely in terms of sine. Now, as I mentioned, in the case of both functions being odd, then you have a choice. You can pick whichever one you want. The functions will be algebraically equivalent. You can actually graph them, and you can see that they can only differ by a constant. In most cases, they will actually function identically with each other, but they could be shifted off sometimes by a constant. That's the only thing that you have to worry about. So if you had cosine cubed, sine cubed, you would get a polynomial in either sine or cosine, because you can follow either of the rules for odd sine or the rules for odd cosine. Now, personally, I would recommend that you use the odd cosine rule because it avoids that extra negative sign, but you will, again, still get an algebraically equivalent expression if you follow all of the rules correctly. Now, let's look at this situation where we have even sine and cosine. So this is our third scenario. In this situation, we're going to have to apply the power reducing identities. So let's apply those right away. So the sine squared is going to become 1/2 1 minus cosine 2x, and the cosine squared is going to become 1/2. Oops. And then 1 plus cosine 2x dx. And so now what I'm going to do is I'm going to first pull out the 1/4, and then I'm going to FOIL. And this is a difference of squares, so I'm going to end up with 1 minus cosine squared of 2x. And I still have a square, so I still can't integrate this. So I'm going to apply my rule one more time. Now, these even powers can end up requiring a lot of algebra steps. So do be careful about the way that you apply the algebra. Sometimes students have a tendency to get carried away and try to pull out coefficients that don't apply to all of the terms and things like that to make their life easier. And I understand the impulse, but it's better to be careful and get the right answer. So if I use the power reducing identity on something that's already cosine 2x, then I need to double it again. So this will now become cosine of 4x. And again, I have to distribute this. So this is the step where sometimes students will, I can just pull the half out. You can't. Because the half doesn't apply to this one just yet. So we're going to distribute 1 minus 1/2 minus cosine 1/2 cosine 4x. And again, depending on the problem, you might get a positive or a negative here. In this particular case, we do get a subtraction, and so we will end up with a 1/2 on both terms. And so we will eventually be able to pull out the half. But if it's a positive sign, again, keep in mind, because then that your constant might end up with 3/2 instead of 1/2. And then finally we can integrate. So let's go down to the next line. 1/8. The antiderivative of 1 is x, and the antiderivative of minus cosine 4x is going to be minus 1/4 sine 4x plus c. Now, if you're just doing a trig integral like this, then this is a perfectly fine way to leave the problem. You started out with x, you're still in x. That's great. If you're doing this in terms of trig substitution, however, which is where this process tends to get applied, you want to kind of think about how to get back to the original variable. And in that case, you will need to apply double angle identities in order to get back. So sine 2x in particular, sine 2x is 2 sine x cosine x. And for a sine 4x, you would then actually get back to sine 2x and cosine 2x, and then you would need to apply one of the cosine 2x formulas to get back to your original x angle, and then you can use your triangle or some of your substitutions for your trig substitution in order to get back to not theta, but your original x variable that you started with. So do kind of keep that in mind. There are several there's actually 3 of them, several cosine 2x identities. And you can use any of them in that process. But as I said, if you start out with x and you're just integrating trig integrals in x, then you can stop here. But if you're using this for trig substitution, you will have to go back to sine x and cosine x, and not sine 2x or sine 4x in order to go back to your original variable.